Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The world of mathematics often unveils its deepest secrets through seemingly simple questions. Among these, the Poincaré conjecture, a deceptively straightforward statement about the nature of three-dimensional spheres, stood as a formidable challenge for nearly a century. Its eventual resolution, however, unlocked doors to understanding higher dimensional spaces in ways previously unimaginable. At the heart of this breakthrough was Michael Freedman, a mathematician whose insights reshaped the landscape of topology. Freedman's journey into the realm of four-dimensional manifolds began in an era where topology, the study of shapes and their properties that remain unchanged under continuous deformations, was undergoing a profound transformation. The classification of manifolds, spaces that locally resemble Euclidean space, is a central pursuit in topology. While mathematicians had achieved considerable success in classifying manifolds of dimensions 1, 2, and 3, the four-dimensional case proved to be stubbornly resistant. The techniques that worked so elegantly in lower dimensions seemed to falter when confronted with the complexities of four-dimensional space. One of the primary obstacles was the failure of the Whitney trick in dimension 4. The Whitney trick, a fundamental tool in geometric topology, provides a way to eliminate intersections between submanifolds. In essence, it allows mathematicians to untangle surfaces that are knotted together in higher dimensional space. The ability to perform surgery on manifolds, cutting and pasting them together in a controlled manner, relies heavily on the Whitney trick. However, in four dimensions, the trick encounters insurmountable difficulties, rendering many of the standard techniques ineffective. To understand the significance of this failure, consider the problem of embedding a two-dimensional disk into a four-dimensional manifold. Intuitively, one might expect that any map from a disk into the manifold could be deformed to avoid self-intersections. The Whitney trick provides a systematic way to achieve this in higher dimensions. Dimension 4, however, presents a unique challenge. The presence of fundamental groups, algebraic objects that capture the essence of loops within a space, complicates the process. The fundamental group's complexity in four dimensions obstructs the smooth application of the Whitney trick, leading to persistent intersections that cannot be easily removed. This failure had far-reaching consequences for the classification of four manifolds. Without the Whitney trick, mathematicians struggled to perform the necessary surgeries to simplify manifolds and identify their underlying topological structure. The landscape of four-dimensional topology remained largely uncharted territory, a vast and mysterious expanse fraught with technical difficulties. Adding to the challenge was the distinction between topological and smooth manifolds. A topological manifold is a space that locally resembles Euclidean space, while a smooth manifold possesses an additional structure that allows for the application of calculus. In dimensions 1, 2, and 3, the distinction between topological and smooth manifolds is relatively minor. Every topological manifold in these dimensions can be given a smooth structure, and this structure is essentially unique. Four dimensions, however, exhibit a far more intricate relationship between topological and smooth structures. Some topological four-manifolds admit no smooth structure at all, while others admit infinitely many distinct smooth structures. This phenomenon, known as exotic smoothness, underscores the unique complexities of four-dimensional topology. The existence of exotic smooth structures highlights the limitations of relying solely on topological invariants, properties that remain unchanged under continuous deformations, to classify four manifolds. While topological invariants can provide valuable information about the underlying topological structure of a manifold, they are often insufficient to distinguish between different smooth structures. This necessitates the development of new tools and techniques that are sensitive to the smooth structure of four manifolds. In this context, the Poincaré conjecture assumed an even greater significance. Originally formulated by Henri Poincaré in 1904, the conjecture states that any simply connected, closed three-manifold is topologically equivalent to the three-dimensional sphere. A three-manifold is simply connected if every loop within the manifold can be continuously shrunk to a point. A closed manifold is one that is compact and has no boundary. The three-dimensional sphere, denoted cis3, is the set of all points in four-dimensional Euclidean space that are equidistant from the origin. The Poincaré conjecture, while seemingly specific to three dimensions, has profound implications for the understanding of higher dimensional spaces. Its resolution would provide a fundamental building block for classifying three manifolds, which in turn would shed light on the structure of four manifolds. A proof of the conjecture would allow mathematicians to decompose complex three manifolds into simpler pieces, making them more amenable to analysis. This decomposition would then facilitate the study of four manifolds that contain these three manifolds as submanifolds. The importance of the Poincaré conjecture stems from its connection to the broader problem of classifying manifolds. Classifying manifolds involves identifying all possible manifolds of a given dimension up to some equivalence relation, such as homomorphism, a continuous deformation. This is a daunting task, as the number of manifolds grows rapidly with dimension. However, by breaking down the problem into smaller, more manageable pieces, mathematicians hope to gain a more complete understanding of the landscape of manifolds. The successful resolution of the Poincaré conjecture would not only provide a powerful tool for classifying manifolds, but it would also have implications for other areas of mathematics and physics. Three manifolds arise in various contexts, including cosmology, where they are used to model the shape of the universe. They also appear in string theory, where they play a role in the construction of Calabi-Yau manifolds, spaces that are thought to be the internal dimensions of spacetime. The pursuit of the Poincaré conjecture and the classification of four manifolds thus represented a central challenge in topology, a quest that demanded innovative ideas and techniques. The existing tools had reached their limits, and a new approach was needed to overcome the obstacles that stood in the way. Michael Freedman, with his groundbreaking work, provided precisely this new approach, ushering in a new era in the study of four-dimensional topology. The allure of the four-dimensional Poincaré conjecture lay in its deceptive simplicity. It asked whether every simply connected, closed four-manifold that is homotopy equivalent to the four-sphere is, in fact, topologically equivalent to the four-sphere. That is, if a four-dimensional space has the same fundamental topological properties as a four-sphere, does it necessarily have the same shape, allowing for continuous deformations? The conjecture had tantalized mathematicians for decades, its elusiveness stemming from the peculiar nature of four dimensions. Previous attempts to crack the Poincaré conjecture, and indeed the broader classification problem for four manifolds, had largely stalled due to the failure of a crucial technique known as the Whitney trick. This trick, a cornerstone of manifold theory in higher dimensions, provides a way to eliminate unwanted intersections between surfaces embedded within a manifold. Imagine two sheets of paper intersecting in space. The Whitney trick, in essence, provides a method to manipulate these sheets, creating a small bubble that allows them to pass through each other, thus removing the intersection point. In dimensions 5 and higher, the Whitney trick works flawlessly. However, in four dimensions, obstructions arise. These obstructions are related to the fundamental group of the manifold and the way surfaces can become entangled. The Whitney trick relies on finding a disk whose boundary lies on the intersecting surfaces. When the fundamental group is non-trivial, or when the surfaces are intricately knotted, finding such a disk becomes impossible, rendering the trick unusable. Freedman's monumental achievement resided in his ability to circumvent these difficulties, effectively inventing a new kind of topological surgery tailored to 4 dimensions. His approach hinged on the development of new techniques for constructing and manipulating topological 4 manifolds, spaces that, while lacking the smoothness of their differentiable counterparts, possess a more flexible topological structure. A central tool in Freedman's arsenal was the Casson handle. These intricate topological objects, named after mathematician Andrew Casson, provide a way to build up 4 manifolds from simpler pieces. A Casson handle starts with an open 2-handle attached to a 4-ball. The attaching region of this 2-handle is a circle. Casson's insight was to consider attaching an infinite sequence of 2 handles to this initial 2-handle, each attached along a curve that represents a non-trivial element in the fundamental group of the previous stage. The resulting object, the Casson handle, is topologically quite different from a standard 2-handle. While a standard 2-handle can be easily visualized as a thickened disk attached to the 4-ball, the Casson handle has a more complicated structure owing to the infinite sequence of attachments. Crucially, Casson showed that these handles are almost, but not quite, standard handles. The almost part is what Freedman exploited. Freedman's brilliant move was to demonstrate that under certain conditions these Casson handles could be straightened out. That is, he showed that it was possible to topologically transform a Casson handle into a standard 2-handle. This straightening process is highly non-trivial and relies on deep results in geometric topology. The significance of this straightening result cannot be overstated. It allowed Freedman to effectively bypass the limitations imposed by the failure of the Whitney trick. By constructing manifolds using Casson handles and then straightening them, he could perform topological surgeries that were previously impossible. The key to Freedman's success lay in his disk embedding theorem. This theorem, a cornerstone of his proof, provides conditions under which a disk can be embedded in a 4-manifold, even when the Whitney trick fails. The theorem states that if a 4-manifold has a small fundamental group, then certain disks can be embedded. Here, small refers to the property of being a solvable group, a technical condition from group theory. The disk embedding theorem is a subtle and powerful result. It does not completely restore the Whitney trick, but it provides a sufficient condition for embedding disks in a wide range of 4 manifolds. This allowed Freedman to perform the necessary surgeries to prove the 4-dimensional Poincaré conjecture. The innovative aspect of Freedman's approach lies in its departure from traditional methods in differential topology. He embraced the flexibility of the topological category, allowing him to construct and manipulate manifolds that would be inaccessible using smooth techniques. His use of Casson handles and the disk embedding theorem represented a paradigm shift in the study of 4 manifolds, opening up entirely new avenues of research. Previous attempts to solve the Poincaré conjecture had largely focused on trying to adapt smooth techniques to the 4-dimensional setting. These approaches had met with limited success due to the inherent rigidity of smooth manifolds. Freedman's work demonstrated that a different approach was needed, one that exploited the unique properties of topological manifolds. The challenges in 4 dimensions stem from the fact that it sits at a critical juncture between the high-dimensional world, where the Whitney trick reigns supreme, and the low-dimensional world, where more geometric and combinatorial techniques are required. 4 dimensions possesses a complexity all its own, a delicate balance between flexibility and rigidity. Freedman's proof of the 4-dimensional Poincaré conjecture was a tour de force of topological ingenuity. It showcased the power of new ideas and techniques in overcoming seemingly insurmountable obstacles. It provided a definitive answer to a long-standing question, and it paved the way for a deeper understanding of the topology of four manifolds. His work stands as a testament to the creativity and perseverance of the human mind in the face of mathematical challenges. It represented a profound advancement in topology, forever altering the landscape of the field. Freedman's resolution of the four-dimensional Poincaré conjecture sent ripples throughout the mathematical community, initiating a period of intense investigation into the nature of four-dimensional manifolds. Before his groundbreaking work, the landscape of four-manifold topology was shrouded in mystery, a stark contrast to the comparatively well-understood realms of lower and higher dimensions. The classification of manifolds, a central goal in topology, had proven stubbornly resistant to attack in this critical dimension. The problems of the time stemmed from the inherent difficulty in visualizing and manipulating four-dimensional objects. Geometric intuition, so valuable in lower dimensions, falters when confronted with the intricacies of four space. The established techniques of differential topology, powerful tools in higher dimensions, faced limitations in the four-dimensional setting. Smooth manifolds, those possessing a differentiable structure, appeared to behave quite differently from their topological counterparts, those lacking such smoothness. Freedman's unique solution lay in his masterful exploitation of purely topological techniques. He demonstrated that, in the topological category, four manifolds exhibited a degree of flexibility that was entirely unexpected. His proof hinged on the construction of exotic topological four manifolds, spaces that, while topologically equivalent to familiar objects, possessed startlingly different properties. These exotic manifolds served as building blocks for understanding the general structure of topological four manifolds. A central consequence of Freedman's work was the complete classification of simply connected topological four manifolds. A simply connected manifold is one without any holes, in the sense that any loop within the manifold can be continuously shrunk to a point. Freedman demonstrated that simply connected topological four manifolds are classified by their intersection form, a quadratic form that captures the way two-dimensional surfaces intersect within the four manifold. This classification theorem provided a complete and elegant answer to a fundamental question in topology, offering a powerful tool for distinguishing and understanding these complex spaces. His proof revealed a profound distinction between the worlds of topological and smooth four manifolds. While Freedman's work provided a complete classification in the topological category, the situation for smooth four manifolds remained, and continues to remain, far more complicated. The existence of exotic smooth structures on familiar topological manifolds, such as the four-dimensional Euclidean space, underscores the subtle and intricate nature of smoothness in four dimensions. The intersection form, a concept central to Freedman's classification, provides a means of distinguishing topological four manifolds. This form is a symmetric bilinear form defined on the second homology group of the manifold, a group that captures the two-dimensional holes in the space. Freedman showed that the intersection form completely determines the topological type of a simply connected four-manifold. This result provided a powerful invariant for classifying these manifolds and opened new avenues for exploring their properties. The contrast between Freedman's topological results and the emerging understanding of smooth four-manifolds became even more pronounced with the groundbreaking work of Simon Donaldson. Donaldson, employing techniques from gauge theory, a branch of mathematical physics, uncovered a wealth of information about the structure of smooth four manifolds. His work revealed that the classification of smooth four manifolds is far more intricate than their topological counterparts. Donaldson's theory, rooted in the study of solutions to certain differential equations arising in physics, provided a powerful lens through which to examine the smooth structure of four manifolds. His results demonstrated that the intersection forms of smooth four manifolds satisfy additional constraints beyond those imposed in the topological category. This discovery highlighted the profound impact of smoothness on the geometry and topology of four manifolds. The combined work of Freedman and Donaldson painted a remarkable picture of four-dimensional topology, one characterized by a striking divergence between the topological and smooth categories. Freedman's results provided a complete and elegant classification of topological four manifolds, while Donaldson's theory revealed the far greater complexity of their smooth counterparts. This dichotomy sparked intense research activity, leading to a deeper understanding of the subtle interplay between topology, geometry, and analysis in four dimensions. The techniques employed by Freedman in his proof of the four-dimensional Poincaré conjecture were innovative and far-reaching. He developed new methods for constructing and manipulating topological manifolds, techniques that have since become standard tools in the field. His work also highlighted the importance of controlled surgery, a process of carefully modifying manifolds to achieve desired topological properties. These techniques, combined with his deep understanding of geometric topology, enabled him to overcome the formidable challenges posed by the four-dimensional setting. The classification of simply connected topological four manifolds, a direct consequence of Freedman's work, has had a lasting impact on the field of topology. It provided a definitive answer to a long-standing question and served as a springboard for further research. Mathematicians have built upon Freedman's ideas to explore the topology of more general four manifolds, as well as to investigate the relationship between topology and geometry in higher dimensions. The distinction between topological and smooth manifolds in four dimensions, revealed by the combined work of Freedman and Donaldson, continues to be a central theme in contemporary research. The existence of exotic smooth structures on familiar topological manifolds remains a source of fascination and a challenge to our understanding. Mathematicians are actively working to develop new tools and techniques for studying these exotic structures and for unraveling the mysteries of smooth four-manifold topology. Recognition of the profound significance of Freedman's work came in 1986, when he was awarded the Fields Medal, the highest honor in mathematics. The Fields Medal is awarded every 4 years to mathematicians under the age of 40 who have made outstanding contributions to the field. The citation for Freedman's medal specifically recognized his proof of the four-dimensional Poincaré conjecture and his classification of simply connected topological four manifolds. The award of the Fields Medal to Freedman was a testament to the depth and originality of his work. His proof of the four-dimensional Poincaré conjecture had been hailed as a major breakthrough, resolving a long-standing problem that had stumped mathematicians for decades. His classification of simply connected topological four manifolds provided a complete and elegant answer to a fundamental question in topology, opening new avenues for research and inspiring further discoveries. The Fields Medal citation highlighted the transformative impact of Freedman's work on the field of topology. His innovative techniques and profound insights had revolutionized our understanding of four-dimensional manifolds, revealing the subtle interplay between topology, geometry, and analysis in this critical dimension. His work had not only solved a major problem, but had also opened up entirely new areas of investigation, shaping the course of research in topology for years to come. The award underscored the lasting legacy of Freedman's contributions and their enduring significance to the mathematical community. The echoes of Freedman's groundbreaking proof resonated far beyond the immediate solution to the four-dimensional Poincaré conjecture. His work served as a catalyst, spurring a cascade of new research and inspiring mathematicians to explore uncharted territories within the realm of topology. The techniques he pioneered, particularly his ingenious use of surgery theory and his meticulous construction of exotic manifolds, became indispensable tools in the topologist's arsenal. These methods provided a framework for tackling a wide range of problems related to the classification and understanding of manifolds in higher dimensions. One particularly fruitful area of investigation that emerged from Freedman's work involved the study of smooth structures on four manifolds. While his initial proof focused on topological manifolds, which possess a weaker notion of smoothness, mathematicians soon realized that the existence of exotic topological four manifolds implied the existence of even more bizarre smooth four manifolds. These exotic smooth structures, which are topologically equivalent but smoothly distinct, challenged the conventional wisdom about the relationship between topology and differential geometry. The discovery of exotic smooth four manifolds led to a flurry of research aimed at classifying and understanding these enigmatic objects. Mathematicians developed new invariants and techniques to distinguish between different smooth structures, uncovering a wealth of unexpected phenomena. Freedman's work provided the essential foundation for this exploration, offering a glimpse into the intricate and often counterintuitive world of four-dimensional topology. Another significant consequence of Freedman's proof was its impact on the development of quantum field theory. Physicists recognized a deep connection between the topology of four manifolds and the behavior of quantum fields. This connection, which is rooted in the mathematical formalism of gauge theory, allowed physicists to use topological invariants of four manifolds to study the properties of quantum field theories. The interplay between topology and quantum field theory has led to remarkable insights into both mathematics and physics. Mathematicians have gained a new perspective on the geometry of four manifolds, while physicists have developed new tools for understanding the fundamental laws of nature. Freedman's work played a pivotal role in fostering this fruitful exchange of ideas, demonstrating the power of interdisciplinary collaboration in advancing scientific knowledge. Beyond his immediate contributions to topology, Freedman's intellectual curiosity and drive for innovation led him to explore other areas of mathematics and science. In the later stages of his career, he became increasingly interested in the field of quantum computation, recognizing its potential to revolutionize computer science and information theory. Quantum computation harnesses the principles of quantum mechanics to perform computations that are intractable for classical computers. This approach holds the promise of solving complex problems in areas such as drug discovery, materials science, and cryptography. Freedman's expertise in topology and geometry proved invaluable in developing new quantum algorithms and architectures. He brought a unique perspective to the field, drawing on his deep understanding of mathematical structures to design quantum systems that are robust and efficient. His work on topological quantum computation, which utilizes the exotic properties of certain quantum states to perform computations, has been particularly influential. This approach offers the potential to create quantum computers that are inherently resistant to noise and errors, a major challenge in the development of practical quantum technologies. Freedman's foray into quantum computation exemplifies his commitment to pushing the boundaries of knowledge and exploring the connections between seemingly disparate fields. His ability to bridge the gap between abstract mathematics and cutting-edge technology has made him a true visionary in the scientific community. He saw the potential for mathematics to address real-world problems and dedicated his career to making that vision a reality. The impact of Michael Freedman's work extends far beyond the specific theorems he proved or the problems he solved.
His true legacy lies in the transformative influence he had on the field of topology and the inspiration he provided to generations of mathematicians. He demonstrated the power of creative thinking, the importance of interdisciplinary collaboration, and the enduring beauty of mathematical ideas. His proof of the four-dimensional Poincaré conjecture stands as a testament to the human capacity for abstract thought and the ability to unravel the mysteries of the mathematical universe. It is a story of intellectual courage, technical brilliance, and unwavering dedication to the pursuit of knowledge. Freedman's work serves as a reminder that even the most challenging problems can be overcome with ingenuity, perseverance, and a deep understanding of the underlying principles. The techniques he developed have become standard tools in the toolbox of modern topologists, enabling them to explore the intricacies of higher dimensional spaces and uncover hidden connections between different branches of mathematics. His insights into the relationship between topology and quantum field theory have opened up new avenues for research in both mathematics and physics, leading to a deeper understanding of the fundamental laws of nature. His contributions to quantum computation have the potential to revolutionize computer science and transform the way we process information. Michael Freedman's career embodies the spirit of scientific exploration and the pursuit of intellectual excellence. He has left an indelible mark on the world of mathematics and science, inspiring countless individuals to follow in his footsteps and push the boundaries of human knowledge. His work will continue to resonate for generations to come, shaping the course of research and advancing our understanding of the mathematical universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.